This lesson is about maximum and minimum of functions of two variables. Similar to the case of functions of one variable that you have seen in Calculus 1, here critical points are important. So first I define what we mean by critical points in the case that we have two variables. Of course, that can be generalized to more than two variables, but here our focus will be on two variables. From the beginning, let me make the assumption that, as a note, the functions that we consider in this lesson have the first partial derivatives. So we consider the functions f of x and y such that the first partial derivatives exist. So with this assumption, our definition of critical points will be relatively simple. So with this assumption, definition, a point AB is a critical point of f of x and y if the partial derivative with respect to x at AB is 0 and the partial derivative of f with respect to y, again at the same point, AB is also 0. So if there is a point in the domain of a function of two variables that the partial derivative with respect to x at that point is equal to 0 and the partial derivative with respect to y at the same point is 0, that point is a critical point of a function. For functions, sometimes they don't have critical points, sometimes they have one critical point, or they might have more critical points. Let's see an example, a simple example. Let f of x and y be defined in this way. Minus x squared minus y squared minus 6x plus 8y. So that's the function, the function of two variables. Now the question is find the critical points. If there is one point, just I write the coordinates of that point. If there are two of them, I separate the points by commas, so I have one other point. So look at the definition. Something is a critical point if it makes the first derivative with respect to x and with respect to y equal to 0. So what I am going to do is I find the first derivative with respect to x. So I differentiate with respect to x and look at y as a constant. So I will have minus 2x minus 6. The first derivative with respect to y, minus 2y plus 8. I set both of these equal to 0. Because if I want to have a critical point, both of these must be 0. So I solve this system. From the first equation, it gives me x is minus 3. From the second equation, y is positive 4. It's a kind of simple system. The first equation of the system only had x. The second equation of the system only had y. Quite simple. So what is the critical point? Just one critical point, and that happens when x is negative 3, y is 4. So therefore, the point with the first coordinate minus 3 and the second coordinate of 4 is a critical point of f of x and y. So the answer is only 1 point. So here, if I want to type the answer, minus 3, 4, 1 point. So just, it has one answer, it's one critical point. Sometimes you might have more than one critical point. We'll see that later in the upcoming examples. But before that, why are we interested in critical points? First of all, let me remind ourselves that we only consider the function that the first derivative and the second derivative exist with respect to x and y. And we are restricted to this kind of function, which include a lot of functions, all the functions that we discussed today. The reason that we are interested in critical points is similar to the situation that was in Calculus 1. For the functions that the derivative with respect to x and y exist, if there is a maximum or minimum, it should be a critical point. Of course, being a critical point doesn't guarantee to be a maximum or minimum, but it is necessary for a maximum or minimum point to be a critical point. Let me show you 3 graphs. Okay, look at the graph on the left. Suppose, first of all, the graphs of functions of 2 variables are not curves, are surfaces. So when I have a function y or z equals f of x and y, the graph is a surface. Just as a reminder, in Calculus 1, a typical graph of y equals f of x, just one variable, was a curve. But here the graph of a function of 2 variables is a surface. Look at that surface that you see. It's a surface, and one part of the surface faces us. We can see that. The other part is behind the scene. It has, in this picture, suppose this is part of that surface. We don't care about the rest of the surface, but at that point that you see, we have a local maximum, meaning that comparing to its neighbors, it's a maximum. So at AB, we have a local maximum. In the graph on the right side, suppose in a part of the graph, we have that situation. So there is a point which is the lowest point of that surface, and we have a local minimum. Also, another type of points that we'll have in the functions of 2 variables, and they're very interesting, are saddle points. Look at this coordinate system, and suppose that's part of the surface of the function of what z equals f of x and y. In part of the surface, we might have a horse saddle shape. I hope you can see that horse saddle shape. That's a very interesting point, and the point that you see there is called a saddle point. If I look at that point with regard to the curve that I just mentioned, I shall show it here. It looks like a minimum on that curve. But if I look at the curve which goes in this direction, and on the other side of the saddle that we cannot see, let me make it dotted points. The same point will be maximum on that curve. These kind of points are saddle points. So in a graph, sometimes it's possible that we might have local max, local min, or a saddle point. For all of these to be a local max, local min, or a saddle point, it must happen at a critical point. It doesn't mean that all the critical points will be one of these. It's possible we have a critical point is none of these cases. But if you want to have a local min, local max, or a saddle point, and we have that assumption that the first derivative with respect to x and to y exists, that must be a critical point. So let me write this as a note. Okay, so this is the note. Consider function f of x and y. Assume the first derivative with respect to x and the first derivative with respect to y exists. For all the functions that we considered in this lesson, or we are talking in this lesson, they do. If f of x and y has a local maximum or a local minimum at points A, B, then the point AB is a critical point of the function f of x and y. Is a critical point of the function f of x and y. But how can we determine that if we have a local, if we have a critical point, how can we determine that if it is a local max or a local min? This is very similar to the situation that we had in Calculus 1, and we used the second derivative test for the determination of a point to be local max and local min. But here is more complicated. It's still called the second derivative test, but it's more complicated than the case of one variable of calculus 1. So I'll write down that second derivative test in the next slide, and then we'll do several examples. So the second derivative test. So to talk about the second derivative test, first we suppose we have one or more critical points. So let's AB be a critical point of the function f of x and y. Here we define a new function out of f of x and y, which is using the second derivatives. So define a new function, d of x and y. It is defined as follows. It is the second derivative with respect to x of x and y times the second derivative purely with respect to y of x and y minus the mixed second derivative with respect to x and y, meaning that first I differentiate with respect to x, then with respect to y. And we had a theorem that under some conditions that works for all the examples that we do. It doesn't matter which differentiation is taken first. The derivative with respect to x, then with respect to y will be the same as the derivative first with respect to y, then with respect to x. So these two second derivatives are the same thing. X and y, and this part is squared. So we define this d of x and y as the second derivative purely with respect to x times the second derivative purely with respect to y minus the mixed second derivative squared. And then we compute this at the critical points. So we have 4 situations. We call them 1, 2, 3. Case 1. If this d at the critical point AB, suppose it is positive, at the same time, the second derivative purely with respect to x at the same point is also positive, then the function f of x and y has a local minimum at AB. This is one situation. 2, if d, the d that you defined in the second line of this statement, if d at a and b is positive and the second derivative with respect purely with respect to x at a and b is negative, then f of x and y has a local maximum at AB. So let me separate these two cases. One case, a second case. The third case, if from the beginning D at AB is negative, then we can conclude that f of x and y as a saddle point at AB. And the fourth part is if D at AB happen to be 0, then the second derivative test is not helpful, is inconclusive. Then if the second derivative test is inconclusive. It doesn't tell us that whether at that point AB we have a local minimum, local maximum, or a saddle point. Of course, to clarify this, we need to do examples, and I have provided several examples that you can watch in the next video.